So yes, thank you everybody for attending. Today is kind of the continuation of a few webinars we've had. We've covered, some introduction to load pull, very load pull basics. We've covered some more advanced topics like advanced waveform engineering with Dr. Tushar Sharma. We've also last week had a seminar on wafer load pull as well. So today we're going to really tackle something, again, it's going to be an introduction, but hopefully we'll try to dive a bit deeper to kind of give you some technical, know-how here. And basically, it's an introduction to active load pull, but we'll be covering some advanced topics. So again, why active load pull? A lot of people think they it's the new thing, and you have to use active load pull in every consideration. So we'll look at that, and then we'll go into some of just the basics, the architectures, closed loop, open loop, things like that. Kind of guide you in how to choosing the right amplifiers and choosing the right components for a setup like this. Then we'll tackle some more advanced topics in form of envelope tracking and DPD and work that's been done with a partner of ours in the UK. So let's get started. So the first thing people always get excited. Let me just close my camera here. Is what is active load pull? As soon as they hear about active load pull, what do they expect? Great tuning range, but especially fast measurements. So here's a quick video of our active system. Basically, let me just start it. So we're entering a value. We're saying at 0.50 phase, and it's hitting the point really fast. You could set up a grid of points, and this is going to sweep extremely fast. Let me just back that up because that's so fast. It's hard to catch it the first time. So you basically define a grid of points, and the active load pull sweeps through these points, blazingly fast. Okay, so that's when that's what people expect. When you think about active load pull, great tuning range and super fast speeds. But what else can you do with active load pull? Obviously fast tuning range, fast impedance tuning, power sweeps. It's not just the tunings that's quick, but also the sweeping the power, getting gain compression curves. You could do lots and lots of curves like that. Let's say you're doing like a Cardiff model, for example, where you're doing a lot of nested measurements, where you're sweeping power across fundamental and harmonic impedances. So that's very efficient for that. You could do not only fundamental but harmonic. You could also look at wideband signals. Passive tuners have been used for modulated measurements for years, but there's some some gotchas that you need to think about when you do that. So we'll look at that. ACRP measurements, intermodulation measurements, EVM measurements, and whatnot. Okay. So again, the question I get a lot is, is active the answer for everything? Do I just use active in every single case? And the answer is yes and no. It really depends on what you're doing. There's different tools, and you have to use the right tool for what you want to do. And we'll tackle that. Passive tuners, we still sell a lot of passive tuners for many different cases and use cases. There's a cost difference as well. So, again, using the right load pull tool for the right application is important, and we'll tackle that in this webinar here. So again, if you've attended one of our previous webinars, we've talked about linear S parameters, load pull techniques, and whatnot. So these, I'm just, I'm not going to spend much time on this, but one important thing to understand is how do you, measuring the A and B waves of a two-port component, using a VNA. So basically what we're saying here is we're going to be using this architecture to kind of measure A and B waves coming out of a device, and based on this information, we'll be able to adjust the signal that we're re-injecting back to the device. Because again, these are slides from the previous one, but here, in the previous ones, we were focusing more on the passive way of controlling the A wave. So, there's three different techniques. You could either, control an A wave with a passive tuner, so reflecting back, with a passive probe, or you're re-injecting it with a coherent signal. So in this case, again, our focus is not the B wave. The B wave is generated by the device. We want to be able to control the A wave going back. So in this case, we're going to look at both. We're going to look at the active, fully active, and a hybrid, which is a combination of a passive and an active signal, being re-injected to the device. Okay, so specifically the active injection signal, as I mentioned, if you look at the top right, you have your DUT that generates this signal. So what we're doing with active is we need to terminate the signal. In the passive, we're actually reflecting that signal back. In this case, we need to terminate it because we have a second signal that's either being fed by, an arbitrary waveform generator. It could be a signal source. There's different ways of doing it. But now we're re-injecting a second signal back, and that's how we're reflecting or sending the impedance back, controlling the A wave going back to the device. Okay, so you could do it, purely active or purely hybrid. Okay, and the reason why people are doing hybrid is because when you go pure active, you need to compensate for the entire mismatch of the device actively. So when you have a passive tuner, that takes care of itself. There's some limitations there. But if you have a big enough amplifier, you could be able to create, a huge mismatch and overcome that mismatch. But again, at lower frequencies these days, tons of amplifiers available, high power, linear, broadband, usually that's not much of a problem. But as you go higher and higher frequency, that becomes more of an issue. Okay. Again, so the hybrid technique, very simple. We'll cover that, more in the seminar. But basically, it's a combination of an active signal, that's fed through the tuners, and the tuners are basically working with the active signal to optimize the tuning range. Okay. So what does an active system look like? Basically, we have our DUT and we have a harmonic receiver, a VNA that's basically has compromised of it has different receivers. So in this case, we need couplers, as we saw in the VNA, the S parameter architecture. So what we're doing here is we're just, feeding the A and B waves back to this harmonic receiver. So anything that's coming in and out of this device will be measured by this harmonic receiver. Okay. Now, in active, you don't have passive tuners. You have amplifiers, right? So you have a drive amplifier that's driving on the input, and you have a feedback amplifier or loop amplifier, load amplifier. People have different terms for it, but basically that's what's creating the A wave that we're sending to the device. Okay, so these are the components that are going to be used to do the tuning, basically. Okay, so again, on the input, there's not much of a change. You're sending a signal through the drive amplifier, through the coupler to the device. And now you're doing the same, but on the loop side, on the load side. Okay, so the DUT will really define what you're going to be using as external components. Passive tuners work the same, low power, high power. You calibrate them using S parameters at very low power, and then you can use them at high power. That's what they were designed for, and they scale very well. Amplifiers are very different in that case. You cannot use a small amplifier to load a very high power amplifier. You need a proportional amplifier on the load to do that. So we'll be looking at that. So again, how do you define the size of that amplifier? So the amplifier and the isolators and all that, that's all in 50 ohm world, okay? So, the devices that we test are normally not 50 ohms, in some cases they can be a very low impedance below, 5 ohms, 2 ohms, depending on how much power, what kind of device technology you're using. So, the feedback amplifier is, as I mentioned, proportionally to the output power and the impedance that you're going to be using or that you're going to be testing. The drive amplifier is normally easier to deal with because it's a small device. It doesn't have to compensate for the gain of the device. Therefore, the drive amplifier is usually smaller or equivalent to the device. But the feedback amplifier is usually much bigger, and you need it to be linear for optimum performance. We'll look into that a bit more in detail. But basically, this is what defines the size of that amplifier. Now, again, at low frequency, this is less of a problem because we have lots and lots of amplifiers available. But at higher frequency, this is a big of a challenge. Now I'm making these isolators blink because, as I mentioned earlier, the passive tuners are very broadband. You can have a tuner that goes from 800 megahertz to 26 gigahertz, 10 to 67. They're very broadband devices. But amplifiers can be broadband, but again, as you increase the power, they become less narrow band basically, and the components that we put in front of them, like these isolators, are basically there to protect the amplifiers, because as we're sending the signals back to the devices, signals are getting reflected back, so we need to terminate that signal back into the load. So those are narrow band components, and we'll see there's more components as we increase the capability. But so if you're going to go from one frequency to another, these are components that you need to look into and swap when you go from one band of frequency to another. Okay. So that was fundamental. Harmonic, how does that work? So same principle on the input. We're not going to change anything there. Again, you're still measuring the A and B waves, and that's a broadband measurement. So those couplers are very broadband. For example, you can have a 2 to 50. You could have, 10 to 67. So those couplers are really relatively broadband, so you can leave them in place. But now what we're going to do is, again, all the signals that we're injecting to the device need to be an active signal. So it needs to be a signal generator that's basically, fed through an amplifier to the device. So initially we only had the fundamental one, so let's just move that one aside. So that's our fundamental amplifier driving the fundamental signal. Usually that's the biggest one because, that's the most significant signal that we're controlling. But now if you want to add a second signal for a second harmonic, well, you have a second amplifier with an isolator, and the same for 3 of 0. Okay, so now you're feeding the signal through these amplifiers, through these isolators, and now you need to combine the signal. So with a triplex or different techniques, but basically these are, again, narrowband components. You might have some filters in there so that you're filtering all these signals. So there's a bit of plumbing that goes around it, but now you could, neatly, feed all these signals into the triplexer, through the coupler, and then to the device. So now you're stimulating the device, not only the fundamental, but at harmonic frequencies. Now you can even push this, further and do something, at baseband, and do all sorts of techniques to basically, tune and stimulate the devices for, to optimize performances. Okay. So let's look at architecture types. So what we mean by that is the closed loop, open loop, and different techniques. So, the closed loop is really the first one that was developed by Takayama. Long method is basically splitting up a signal. So you're splitting up a signal. One of them is being terminated, as I mentioned. The other one goes through it, the closed loop. And then we could play around with the phase and the magnitude, and the amplifier basically amplifies that signal, sends it back to the device. Okay. Now this is a closed loop architecture, so it is, susceptible to some oscillation. There might be some leakage in the coupler or the isolator that you use. So all of a sudden, if not taking, consideration, you could run into some oscillation, which could damage the system or even damage the device. So, a technique that we've also used currently and in the past is a quasi closed loop. So what does that mean? So we're breaking the loop because what we're doing is, again, we're, taking the A and B waves through the couplers, sending it through our down converter. If we just took the traditional closed loop technique, we basically don't down convert it. We just, feed it through the loop and we send it back. But what we do here is we, down convert to baseband at a lower frequency. We have an FPGA that computes that and treats this information and basically recalculates the I and Q that needs to be up converted again and sent back to the device. So again, this is a big advantage because you're in real time. You're monitoring what's going on with the device, and with the FPGA, you can do also some sort of advanced math. You could do a lot of measurements. This is where the heart of the IP of tuning and measuring like these broadband signal goes into. So this again it's called the quasi closed loop because we're breaking that RF and chain going to the IF before we up convert it back to the RF. Okay. So the open loop is, different in the sense that now we're not splitting up the signal. We have two coherent, synchronized sources that we're injecting, from a different path. Okay. So now, this also has some advantages and disadvantages. The case here is you're not actually monitoring what's going on of your device. If your device changes drastically, you don't necessarily know exactly where you are. So you need a few iterations, extra iterations to get to certain points. But basically here, this is less prone to oscillation in this case because, you're basically controlling a signal that's not being affected by a signal that's being fed in. So Again, this, I just put this one up just because, again, people are always asking me like, well, should I always do passive? Should I always do active? What kind of things that I should do? So again, the passive, the complexity, is relatively low, relatively simple. Cost is, mid to low. The gammas, depending on what tune type of tuners you want to use, will be limited by loss. So, obviously you can't cover the entire Smith chart. Speed is relatively low depending on what, compared to active, because you're mechanically moving the tuner and moving the probe inside the tuner. So that takes time to actually move the tuner physically. In terms of power, yes, the passive tuners are hard to beat because they can support low and high power. Modulated, we'll get into that, but theoretically they do not support modulated signals, okay? Active, again, complexity is high, but once you're set up, you're good to go. If, once you've figured out all your power buttons and whatnot, usually that's not too much of a problem. The cost can be high, again, depending on the power, the bands and whatnot. So that's to be expected. But again, you're investing in the tuning range and the speed. Bandwidth, well, now you could also do, some modulated signals. That also comes at a cost, but if that's really something you really need to tackle, the active is the way to go. Okay. So we've been talking about these amplifiers and how do we choose these amplifiers? This is, it's easy to say, oh, just use the biggest amplifier, but sometimes the managers will say, yes, the largest amplifier is the most expensive one, so that might not be the solution. So ideally, you want to work with, linear amplifiers, both on the input and on the output. Let's talk about the input first. So the drive amplifier on the input, obviously you don't want to overdrive that amplifier, too much, because if you're measuring, signals where, you want to optimize for harmonics, you want to optimize EVM, linearity, and things like that. If you're working with an amplifier that's fully compressed and like 6 dB compressed, and there's like screaming harmonics out of this thing, what are you actually measuring? Are you measuring your device, or are you actually measuring the performance of your driver amplifier? Same goes for the output. Now, the output amplifier needs to also, as I mentioned, be higher power than the input. So usually what that ends up being is you have less dynamic range, you have less power range, you have less frequency coverage. So what you end up having is you have kind of a mismatch. You have a very broadband, high gain input, but lower power driver amplifier. But then you have a more narrow band, less, less, I want to say less capability. It has more power, but it has a smaller window of operation. So what happens in this case is, like, now as we drive, again, we're driving both the input and the output at the same time. As we drive the signal on the linear region, these are operating together. This is great. So as I compensate the input drive, the output drive is compensated for it, very linearly, and I'm hitting my targets, very closely, easily. That's fine. But now as we continue moving and we continue driving it, now you'll see that the output power of the feedback amplifier will start dropping. And now you need to overdrive that amplifier. And you'll see at one point you can't even get enough power. Therefore, the increased tuning range you were expecting couldn't even get there. So as I increase the drive here on the left, that's going, but on the right, whoops, I'm stopping and I'm running out of power. So then you can say, okay, well, what's the fix for that? I'll just like increase the amplifier, which again, it's not as simple as we mentioned. So let's take a few examples. I'll take some real numbers here. So this is like the input power budget. Okay, so again, this is just a chain. You have your source on the input. You have a driver amplifier. You can have a bias T, coupler, isolator. So you have a bit of a path there. So obviously, to get the power delivered at the device, you need to know what that insertion loss is going to be before the device, but the impedance, that you're going to be, that you need to overcome will create a mismatch loss, right? So you need to overcome that mismatch. So, but as I mentioned, on the input, it's less of a problem because, you don't have the 10, 15 dB gain of the device that you need to overcome. It's much lower power. And in reality, when you have a vector load pull like this, because all active systems have a, vector capability, you're actually measuring the impedance of the device. So what kind of power available is to the device and what delivered power, you can calculate that. So it's less of an issue on the input. Now, mismatch loss, many people, underestimate how important that number could be. And when we do it with tuners, you're basically creating that mismatch with the tuner, so you don't necessarily need to worry about the loss in terms of the tuner. The tuner takes care of that. Okay, so here's a quick table of what is values of an insertion loss. So on the right, you see the chart that basically you see the mismatch loss, increases not linearly, basically exponentially. So what we're seeing is at 50 ohm, let's say I want to inject, power at 50 ohm. Well, then you're just looking at normal 50 ohm insertion loss. So there is no mismatch loss at 50 ohm. As you reduce the impedance, or as you, create a mismatch, now we're just giving an example from ohm and going towards 1 ohm, you can see that the mismatch loss steadily increases, and until you get to 0.7 gamma, you're looking at less than 3 dB. So again, depending on what frequency you're operating in with, and the power levels you're operating, it's not so bad. But as you get to 4, 5 ohms, 2 ohms, now the mismatch loss gets like, greater than 5. You're looking at, we even have an example with 1 ohm, and now you have a mismatch loss of 11 dB, which is pretty significant, especially if you start operating at the higher frequencies, where every dB of power gets extremely expensive. So again, let's look at it on the output side. So now we're looking, going on the other direction. So what are we doing here? We're looking at the output power delivered to the load, okay? So now we need to match this power and even actually overcome this power with the mismatch loss. So depending on what impedance the device is going to be, we need to not only match the power, but compensate for the mismatch loss created by the device, okay? So obviously there's the insertion loss of the coupler and components that are there. So obviously you want that amplifier to be as close as possible, because you don't want to add extra loss in that whole path. But that will be a total of it. So let's see 2 examples. Okay, this is a 2-watt device, and the next slide is going to be a 10-watt device. It's just to kind of explain what numbers we're looking at here. So there's 2 examples here. What we did is, let's say we have a device that has a 5 ohm impedance and a device that has like more forgiving 7.5 ohm impedance. So let's just take one example here, the lower case. So let's say my device is a 2-watt device, and it's outputting 2 watts, and it needs to be matched at 7.5 ohms. Okay, so what kind of amplifier do I need to be able to overcome that? So the mismatch loss is 3.5. Now let's say we have a very low insertion loss coupler, isolator bias T, let's say of 0.1 dB. So to match that device, a 2-watt device, you need roughly a 10-watt device. So as I mentioned, you don't want that to be PSAT, because then you're going to be operating with a feedback amplifier that's going to be, greatly compressed, creating all sorts of nonlinearities. You're going to have to have a very elaborated tuning algorithm to be able to compensate, because as the feedback amplifier is nonlinear, you try to set a certain power, but it's actually not going there because it's being compressed. So you need to overdrive it, drive it, and ultimately that's going to be a problem. Again, now I'm sounding like a broken record. A 10-watt amplifier at 2 gigahertz is not too difficult to find. Very linear, you could find that easily for a few $1,000s. This is not really a problem. Let's look at the 10-watt one. Now, a 10-watt device, being matched at 2 ohms. So let's take the top case in this case. So now I have a device that needs to be matched at 2 ohms, and the output power is 10 watts. So now all of a sudden, the mismatch loss is 8.3 dB plus an insertion loss of, again, let's say roughly 2 dB, for example. Well, now you have a total loss of 10 dB. That's a huge problem, because now, instead of having like going from a 10-watt device and having a loop amplifier of like 10, 20, 30 watts, you're looking at a 100-watt amplifier. So again, even at 2 gigahertz, these are, you could find them. That would be pretty much narrowband, but it's doable. You could find those. But again, if you go into like higher frequency, you look at the 5G applications in mmWave, you're going to have a tough time to find an amplifier that has more than 10, 20 dB that's affordable. Okay, so this is something that people always kind of take for granted. They think that the active will just take care of itself, but there's a lot that goes into finding the right windows of operation, both on the input and on the output for these kinds of applications. Okay, so how can I reduce the power requirement? Obviously, there must be a way to do that, and we kind of alluded to it before. So again, it's the hybrid method. So hybrid method is, it says it's a combination of passive and active. So what we do here is we put a tuner in the path. So the tuner, instead of, we don't take the tuner all the way to 5 ohms. So what we do is we put it at a midway point where the mismatch loss of the tuner is relatively low. So then you kind of, minimize the mismatch, but you also minimize the loss. So now so you basically feed that signal through the tuner, and now the tuner and the amplifier are working together to meet that 50 ohm. So that reduces the feedback amplifier requirement. So if we look at it in terms of Smith chart, so again, we're always interested at the DUT reference plane. We talked about it in the previous webinars. The passive tuners have great tuning range at their reference plane. As you add a cable or anything, you're reducing that tuning range significantly. So let's say these are the load pull contours that you want to optimize at a fundamental impedance, and you have a passive tuner. So the passive tuner, I had to put a cable, I had to put a probe. So this is the tuning range of the passive tuner. So clearly, if I do load pull on the device, not only am I not going to get close contours, but I'm actually not hitting the maximum point. Okay, so in this case, we have a designer that is designing this great amplifier, is trying to tune it with a fundamental passive tuner. He's not getting that. So what do? Is we put, an active loop in the back. So we take the tuner and we set it as a pre-match so that it brings this tuning range closer to the optimum point, and then the active component takes care of the rest. So now they're going to work together. So now we're shifting this fundamental point, or the center point, closer to the optimum point, and now the active takes care of the rest. So again, they're working together to be able to meet that that optimum point. Now, but when I look at this, I don't want to say it's a problem, but there is a bit of a compromise. So now we basically push this tuning range out, but the tuning range is only in one area. So we're not covering the entire Smith chart. We're just focusing on one point. So this is great if we just have we're looking for maximum output power, and that's the point. But what happens if I have a different point where the contours for, I don't know, efficiency are somewhere else? So now you won't, basically, if you use this center point, you won't be able to close the other circles. You're barely cover the other points. So what we end up doing is you move the passive tuner to that point. So now when you do the load pull, you don't just focus on one area. It's the combination of the passive tuner and amplifier that allows you to go pretty much anywhere you want on the Smith chart. And again, now the amplifier doesn't have to work alone to create the mismatch loss. It's the combination of the passive and the active. So this is, I've got some mixed feelings from customers. Some of them say this is the best of both worlds, and some of them are like, oh, well, this is the worst of both worlds, because now I have to deal with the active and the passive. But again, it really depends what you want to do. This is a scenario where you're capable of having a smaller loop feedback amplifier combining with a broadband tuner, which, for example, might be able to do fundamental but harmonic as well. So a lot of people, what they like to do is they really focus on optimizing the fundamental impedance, combining the passive and the amplifier, and then doing some harmonic tuning using let's say a 3-frequency tuner that allows you to do very flexible measurements at the fundamental while holding the harmonics at specific impedances. Okay, so I guess anybody who's been watching our stuff and been following Focus for the past years, our delta tuners, these are our high frequency tuners. They're passive tuners that have very high tuning range and basically connect directly to the probe tip. So, customers will say, well, do I even need, hybrid for these type of tuners? We have great tuning range. Here's an example of, we have a harmonic tuner, 10 to 67 on the input, 10 to 67 on the output. So you could have fundamental, pre-match, harmonic, 2-frequency, 3-frequency tuning using these systems. So, there is no cable in this case. So do I even need to go active? Here's an example of the tuning range of a delta tuner at 40 gigahertz. So again, here we just basically did some load pull on the through, so there's no device here. Just we want to see how far we could push the tuner. So again, depending on the residual reflection of the probe, of the bias T, of the entire component, some of these circles are a bit shifted. So here we did like low pull just to see the maximum tuning range we got. So as you can see on the, if you look at the source tuner on the low side, we could get to 0.85. But now the same tuner, if you go 180 degrees, we're limited at 0.775 gamma. Okay, so in certain, and this is at 40 gigahertz. So in certain cases, that's good. That might not be enough. So, but it's still very good compared to what was previously available. But when you do measurements in certain cases, here we have output power and efficiency contours. So on the left, you see that the output power contour is not closed. We're getting very close to the center. It seems to be, we're not far off. On the right, though, you can see that, well, there's still ways to go to actually close those efficiency contours. So clearly with the passive, for this device, it's not enough. You need to push it a bit further. You need a bit more tuning range. So what we did is, again, we did the same measurement, but now P out and efficiency with a hybrid technique. So again, kind of combining an active signal with a passive signal. And you can see that on the left, we fully close it, on the right as well. So now let's compare. We see here we're overlapping the active, or the hybrid, and the passive. So you can see that they're perfectly overlaid. And you can see that clearly on the efficiency point with the passive tuner, we weren't getting there. So in this case, we were able to use a smaller amplifier. If we would have done this purely actively, this would have taken a much, much bigger amplifier to match this, because now that mismatch loss is very high. We were looking at the mismatch loss, going from 50 ohms to 2-3 ohms. Well, this is almost an example of this. You're going from 50 ohms, or let's say 0 gamma to, this is probably like 0.85, almost 0.9 gamma. So to overcome that mismatch with an amplifier is doable, but it can become very expensive. Okay, so that's really, that was really looking at fundamental load pull, CW load pull, but again, fast CW load pull. But a lot of people are looking more and more at modulated load pull. So for years, it's not active. Modulated load pull is not new. We've been doing it with passive tuners forever. But why has the active been a bit more interesting now for these signals? Is if you look at previous bandwidths, they were relatively small. If you're looking at a 1 megahertz signal, 5 megahertz signal, even 20 megahertz signal, when you use a passive tuner, the passive tuner has a broadband response. So you're not just presenting a single impedance, you're actually presenting an impedance skew. Okay, so before, why were designers and test engineers not too worried about this? Because the impedance was relatively, it was a few degrees, so, but as LTE came on board, we're talking about 5, 10, 20, 40, you have dual carrier LTE. All of a sudden this, the bandwidths that we are presenting the impedance are being skewed, and you're not really presenting a real scenario to your device. So you could be getting some results on your on your setup, and then when you end up designing it and putting it in a final product, you can say, well, wait a second, there's the discrepancy here. I'm not getting the results I was expecting. So now, as Wi-Fi, WiGig, and like these 802.11 ACs and these like wider signals, now you're looking at 80 megahertz. And if you even look at the literature of 5G, potentially you're looking at 500 megahertz, 1 gig, 2 gig. So this bandwidth will increase dramatically as we move forward. So now the problem is, if we look on the right, this is just an example, hand drawn example, but you could be presenting an impedance that's going like once or twice around the Smith chart if you're looking at 2 gigahertz signal. So how accurate is that, or how realistic is that, or even how usable is that when you're using a passive tuner and your impedance is basically, going around the Smith chart a few times, right? So what affects impedance skew? Like obviously, if you have a single carrier, a CW signal, you have a single dot on the Smith chart. That's represented by this multiplication sign here. So as you increase the bandwidth, the signal that you're presenting will have a certain impedance skew. Okay, that's one factor. And as I increase this bandwidth, the bandwidth increases, the skew increases, directly proportional. Okay, and again, the wider we go, the greater the skew. Okay, this is basic math. We can calculate that. We know exactly what kind of skew we're presenting. Okay, but there's also an electrical length component to this. So as I increase and I make the, I have to increase the electrical length by adding a cable, well, then this impedance will also be longer. So this is a problem as we get greater bandwidths of signals, and now you're presenting impedances and doing load pull. Now you're not presenting, a small tight impedance. You're presenting a very broadband impedance, and how do you interpret that in a measurements system is still to be debated. So here's an example. This is just, 2 examples I have. I have a 25 and a 40 meg after. So this is a 25 megahertz signal. So we're measuring, basically what we're doing here is we're measuring the S parameters across 25 megahertz at the tuner reference plane. So on the left side, we're trying to tune the impedances, very low impedance. So we have a bit of a skew. It's 25 megahertz. So even if we're at the tuner reference plane, the probe that we're presenting is not like directly connected to the connector. So it's maybe a few centimeters, an inch away from that that reference plane. So the impedance skew is relatively small. So as you add here on the right, we see a 12-inch cable. And now at the end of this cable, for the same 25 megahertz signal, that impedance skew gets much larger. Okay. Now some people will say, well, 12-inch cable is very long cable, but I've seen scenarios with a 3-foot cable. So this is just to give you a bit of a feel of how much of a phase shift you can get by adding some electrical length between the tuner and the device. Here's 40 megahertz, so proportionally bigger. Again, on the left, relatively small, but you're talking about 40 megahertz versus, 40 megahertz on the right. So this is a problem. If you have a, if you're characterizing an amplifier and you're saying like, okay, I want to do a constant VSWR measurement, okay, that might not be too bad. But now if you're trying to optimize for EVM or ACPR and whatnot, well, you're presenting a very different impedance across this bandwidth. And how true will that stay in the final design? So again, I'm not going to spend all more time really on the delta tuners, but the delta tuners, people will assume, well, the delta tuners connect directly to the to the device, so that's fine. I don't have this cable length, but you still have the probe length that's there. So what we did is we want to see like how could we basically look at this and say like, will the modulation or the EVM ACPR measurements be affected by a passive tuner impedance? So here we look at modulated load pull. So modulated load pull, we basically just fed a modulated signal through the input tuner and to the output tuner. And on this, we basically tuned the fundamental, and we knew that we were presenting different skews. And for the different skews, we looked at, what was the EVM performance. So again, we have fundamental tuners on the input and output, and we're measuring this, the ACPR and the EVM on the output. And these are basically the impedance that we're presenting to the device. So you can see that, we have, the phase shift is always pretty much the same. So these are impedance skews for 100 megahertz. So at 0.4 gamma, 0.6 gamma, 0.75 gamma at 140 degrees, you could see that there's a roughly 15 to 16 degree phase shift. Okay. So when we're going to be doing load pull, that's what to be expected. Okay, 200 megahertz, well, no surprise, it's twice as large basically in terms of impedance skew. So what we were able to see is that even if you look at 50 megahertz, 100 megahertz, 200 megahertz, 400 megahertz, we overlaid the EVM curves, and they were very close. You could see that the EVM values didn't seem to be affected by the impedance skew. But this is something that this was a one-time device that we looked at. And we're looking at more devices. So this was not, we're not saying that, yes, this is, will cover all cases, but does provide a bit of information on how usable a passive tuner would be for these type of measurements, okay? Now, another thing to think about when you actually do like active measurements is, the signal to noise ratio will change as you go from a CW signal to a modulated signal. So this, I just copied this from a Keysight app note that kind of describes this, the effect of the dynamic range and basically tied to the signal to noise ratio when you go from a one-tone signal to a multi-tone signal. Because as you increase the bandwidth, you're effectively, you know, reducing the signal to noise ratio, which is drastically going to reduce the dynamic range. So the reason I mentioned this is people will say, well, I want, you know, very high bandwidth and very large bandwidth, and I want very great dynamic range when I do load pull. But effectively what happens is, here's an example of, let's say we're doing some active load pull here. So this is a 20 megahertz signal that we're basically tuning around the Smith chart, and we're measuring ACPR while we're doing this. So obviously, you know, we're measuring a broadband signal and we're reducing the dynamic range. So the ACPR and EVM values, you know, will be good, but they're not going to be in the -50s and -60 dB range. You know, they're going to be, you know, roughly 45, you know, depending on that. Same thing for the load pull accuracy. You know, that you're using a very broadband digitizer to measure, and you're re-injecting this broadband signal. So you end up reducing the dynamic range versus, you know, if you were using a CW signal where you have like greater than 60, in certain cases, greater than 80 dB dynamic range. So, but again, this is ultimately if somebody wants to have like a very, you know, controlled impedance. So what we're seeing here in the load pull is we're not presenting a skewed impedance like a passive tuner. We're really controlling the impedance across the entire bandwidth, setting a single point. Okay, so this for some customers, this is crucial. You want, you know, that fixed impedance, measuring ACPR accurately, and measuring EVM. So now we'll talk, you know, this is kind of the final part of the topic, and this is getting more and more, you know, traction. I invited one of our application engineers out of Missouri, Dragon, to be online if there's some more technical questions. But, you know, just to recap a bit, you know, envelope tracking, if people are not familiar with it. So what envelope tracking means is you're basically, you know, modulating, or you're controlling the drain bias. And you're basically not leaving it on the whole time. You're basically modulating it so that when you're actually, you know, the device needs that drain bias, it uses it efficiently. It's not just totally on. Therefore, when you have low power, the efficiency and the gain is very low. You're optimizing you're utilizing this modulated bias to optimize the performance. And we're also applying DPD. So what we've done is we've worked with the Cardiff University, and obviously they're very, you know, they're experts in nonlinear measurements, all sorts of nonlinear load pull and whatnot. So what they wanted to do is to use, you know, our rapid system. This was our first iteration of rapid system, which had roughly about 40 megahertz of bandwidth, but this was kind of a proof of concept. And basically what they were doing is they were able to do load pull and control, you know, with the envelope tracking, and do some DPD in non-50 ohm measurements. So in this case, you know, let's take a quick look here. So this is, you know, again, this is a zoom picture on the right, and this is the architecture. So the architecture can be divided by two. So on the left, there's the NI hardware. So that, you know, is comprised of, you know, an PXI chassis that has a, you know, computer controller in there, but is also comprised of a VSA and a VSG. So it's what they call the VST, and it basically has both the signal generation and the analysis, but also we have a real-time FPGA in there. So the real-time FPGA is linked directly to our down converter and up converter. So as you saw if you look at the Quasi loop architecture, this is what we call the Quasi loop, where we basically use the RF signal down converted and send it to the FPGA, and we do some math on it, and we can do some very advanced tuning algorithms to do this. So again, on the left is the NI hardware, on the right is the Missouri hardware. So on the picture, you can see that the grayish white components are from NI, and on the blue are the Missouri up and down converter. And this is actually two frequency system. So there's two tuners in this case. There's the fundamental and the second harmonic as well. Okay. So what did Cardiff do in this case? They basically, again, they used our architecture, but they were focusing on modulating the supply. So they have an AWG that's, you know, has some algorithms that's going to do all sorts of things. It's basically it's not going to be a fixed DC bias. It's going to be able to modulate that going through the bias T on the output, modulating that drain voltage. Okay, so there's all sorts of, I'm not going to go too in depth with this one. Dragon might answer some questions if you guys have, but basically the goal here was to see what we can optimize. We can optimize efficiency, we can optimize gain for various envelope tracking methods. So here is two different load pools. So we did one load pool with a fixed 28-volt bias. So again, we're doing load pool and we're not changing, it's a fixed 28-volt bias, and we're looking at the efficiency. So in this case, you could see that the second scenario where we did use an envelope tracking, we were able to optimize it and increase it by around 18%. So, there's two overlapping curves. You see one of them seems to be like over 48% and the other roughly 47%. The other one is drastically lower. So you can see that, with this technique, they were able to increase the efficiency drastically. And again, this is all being done with active load pull. So we're tuning the impedances, not only at the fundamental, at the harmonic. Now here we're just showing fundamental, but we're optimizing not the harmonics for efficiency. We're just optimizing the bias algorithm to get better efficiency. So again, they went a bit further. So on the left, there's basically three different shapes of how they fed the bias or control the bias of the drain to kind of get the different performance of the devices. One of them is basically, the optimum gain. So let's say you want a flat gain. So as you adjust the drain bias, you could get a constant gain across the whole power. The other one is, basically the optimum efficiency point. So the lower curve is the one that basically drops down, but then brings back up. That really gives you the optimum efficiency point. And there's also a trade-off where you kind of sit between both, and you can all optimize the algorithm to get the best of both worlds. Okay. Again, looking at comparing the different methods here. So again, there was the 28-volt fixed version, ISO gain, a trade-off, and optimum efficiency. So here are the values. The output power is pretty much all the same, but you can see the efficiency and the EVM values are strongly different. And again, when we apply DPD, the ACPR measurements are also vary depending on which one you're using. So the final note here is, and I'm sure we'll have some more questions on this, I want to keep a bit of time for a Q&A, is, we were also able to not only do envelope tracking, but apply DPD, NI's DPD linearization algorithms, not only at 50 ohms, but across frequency, across the impedance space. And you can see here on the right, there's different ACPR measurements where we're showing like the optimum here on the left is, minus 48 dBc versus on the right is like, roughly minus 40, minus 41. So definitely an improvement if you would have not used the DPD algorithm. So that's, I want to keep it less than 45 minutes. I went a bit above time, but that's it for today. Again, there's probably going to be a lot of QAs. I haven't looked at I haven't been monitoring the chat, but I think now we could open it to chat to see if anybody has any questions specifically on this.